I measured them all there.
Good. Hello.
I was eating and they were starting to actually check their plates. Yeah. All you have to do is put some stuff on the line.
Dr. Mike, do you think Jim Bernier
yes, I don't know who bought these for me, but I suspect it's this class, so I should say thank you to somebody. But they showed up in the lab on Thursday.
Did it have a little note saying, here you go, Dr.
You know, it didn't have a note, so I just stole someone else's. Yeah, no, I looked and wanted to check I got the right thing. Yeah, and I wanted to make sure that I wasn't taking somebody's. So now you guys are making me second guess. That maybe I. All right. Oh, good. Are we at start time? Okay. Hey, good. Let's continue on where we left off. I'll start by saying, as you were commenting, thank you. I think somebody in this class bought me these pins. Is anybody? Thank you. Is it this class? But these just kind of showed up, and I was in lab Thursday, and I was checking around. So, anyways, I'm going to try these pins. So, thank you. Or maybe I should try my other class here. But I'm assuming it's this class, but I don't really know here. Anyways, so I got some better pins here. Let's keep going where we started, or left off, I should say. It was chapter 27, and 27, I think, by far is the easiest chapter we've seen so far. It is trying to get across to you what is this idea of current and resistance, and how are they coupled together, or how are they related together, is what we called Ohm's law. So a good practical application of all this great electrical field stuff we've been learning in the first 3 chapters have been chapter 26 and now 27. 26 was our capacitors, and 27 now is with our resistors and our Ohm's law. And so I trust that you recall that. Here's what we came across. This was the lesson of chapter 27, and so I thought today we would do a few examples from chapter 27 and then move into 28. And 28 is kind of a continuation where we put, instead of one resistor, multiple resistors, and look at some consequences of that. And that'll be our next chapter. And so these 2 chapters, 27, 28, obviously go together, and they have to be part of our circuitry, part of our electronics stuff. Then we're about halfway through the semester, so then we'll switch into magnetic fields at that point and start talking now about magnetic fields, now that we've got a good understanding of electric fields. But just to recap, here's what we learned. We did learn what current is. Current is the rate of flow of charge. And so it depended on 4 factors. It depended, of course, on how fast they were moving. That hopefully was obvious. But their concentration, their cross-sectional area, the charge each one has, you put those 4 factors together, and that's the rate at which charge is flowing. And that's what we called current. And that was the point here of this chapter, was to break it down to the point of what is current on a microscopic level. And I think we got a good picture of that. So that was one idea. The other idea was then what is opposing the current from flowing is what we refer to as resistance. And we hopefully saw 4 reasons for that too. One was the material, the temperature, the length of it, and the cross-sectional area. Of course, the other factor we didn't discuss too much in this chapter because we've already had a good understanding of that, but that was the voltage, where the energy came from or where the force came from that pushed them to begin with. And so we finished off with saying that these two together, that is the push and the stopping, determine how much flow. And that was the whole chapter in a nutshell, yeah.
In the homework, there was a question where you were supposed to know N, and I think it's supposed to copper was like 8.
Oh.
Is there a way that we can solve for that? Do we have an equation for that? Or
Yes, they do want you to be able to figure out N, and what they want you to get that from is the density of it. So there is a little bit of chemistry that you may or may not know, so you may argue that it's not a fair question. I can say this much. I wouldn't put that kind of requirement on the test, so I wouldn't expect you to know it for the test. But here's what they were after in that problem. They want you to look up here at copper, okay? And then copper, if you look on this periodic table, or what I'm going to do and as an example problem, I'm just going to turn to chapter 14 where we have listed all the densities, okay? Now the density, of course, just tells you how much mass per volume. But if you look on the periodic table, from the mass per volume, we can then figure out how many atoms we have per volume. Then the last piece of that is we know from chemistry, not from this class, but that we are going to get 1 electron from every atom. So if we could just find out how many atoms per volume, then we would get it. Okay, and so it would look something like this. You would start off by looking up what is the mass per volume. And then from there, you could look up 1 atom and how much mass you have per atom. And that's where those two come in together. Because when you multiply those two together, you are now going to get the number of atoms per volume. Realizing that there is 1 electron for each atom, we then have this number there.
Yeah, it's aluminum or something that's...
Yeah, and then of course, if it's aluminum, then you have to stand back and say, okay, how does aluminum work? And even copper's a bit more, well, maybe, I was going to say aluminum's more complicated, but no, I think copper is a bit more complicated too. But then aluminum, then I would take that and go times the number of electrons per atom. Which in the case of copper, it's just 1, but in the case of aluminum, it's 3. And so again, that's where that extra step of little bit of chemistry would have to come into play. And so I think we only do that one time and say, yeah. All right, so with that in mind, I thought I would try a couple of examples. Again, I don't think this is going to be too overwhelming stuff. We'll make it a little bit more advanced as we get into the next chapter. But this is our fundamental. This is what I said. These 3 chapters, 26, 27, and 28, are our applied chapters. So we learned a little bit about capacitors and the purpose for capacitors. Now we're going to learn a little bit about resistors and the purpose of the resistors and the idea behind the resistance and the current. And then finally in chapter 28 here, we'll put a lot of this together. We will say, well, what happens if you have more than one resistor? And what gets very interesting at the end of chapter 28 here is what happens if you have resistors and capacitors in the same circuit. And so what are some of the features we can get there before we go on to magnetism? All right, well, as I said, I'd like to do number 7 here as the first one here. And no, actually, how about number 1 instead? I think number 1's a little more enlightening. I kind of listed them both there and decided this morning not to do both of them. I think they kind of say the same thing here. But it just says this, that in a particular cathode ray tube, the measured beam current is 30 microamps. How many electrons strike the screen every 40 seconds? And so a cathode ray tube is just where you take one side and you charge it positive. Maybe I'll just take a little wire here and maybe kind of imagine hooking a battery. But if one side then gets to be a positive charge and the other side is then negative, if you've got this negative enough, or as you'll see in some of the labs we're about to do, we then heat it really hot. So we first hook it to the negative side of the battery, then we heat it so much that the atoms move so quickly that they knock the electrons off. And so if we knock the electrons off and we put this whole thing inside a tube that is evacuated, so there's no air molecules in it, what will happen is when one of these electrons get free, of course, they are then attracted to the cathode, and hence it's called a cathode ray tube. And so the electrons can be moving very, very quickly in here. And so what they are just trying to get you to see here is we do have some current. And so this being our first example is the one that, look, this is the basic idea of current. What is current? Current is the flow of charge, and what they are saying is this is 30 microamps. And so I picked it for a couple reasons. The first one is just to make sure you get the physical understanding of what is current. Current is the flowing of this charge. The charge then is flowing is made up of billions and billions of electrons, and that's our question. After 40 seconds, how many hit the screen here? And so maybe it's best to write it as 30 times 10 to the minus 6 for the micro. And for an amp, let's write this as coulombs every second. Because I think, as you can see, the first question might be how much charge. The charge would be the total sum of these electrons over time. And so if we apply a little bit of our calculus here, we can just add up the rate over a period of time. It is a constant current, so this just becomes current multiplied by time. And so how much charge actually strikes there is the current multiplied by time. Well, the current is our 30 microcoulombs every second. And so if we let that current go for 40 seconds, the 3 and the 4 is a 12. Times 10 to the minus 6. Seconds cancels off, and that's coulombs. And I guess we can reduce this to 1.2, and then 1, 2, 3. So times 10 to the minus 3 coulombs of charge. So 1.2 microcoulombs is how much charge would hit after 40 seconds. So we're almost there. Obviously, there's one more step, because I think, let me just double check here, they asked how many electrons. Okay, and so this charge must be equal to, I'll call it n, the number of electrons, multiplied by the charge of each electron. And I suppose I should be careful here. I have done things in absolute value, and so when I make my next step n, I'm just going to put 1.602 times 10 to the minus 19 coulombs, and I won't do a negative number there. But it's going to take quite a few electrons to get this 1.2 millicoulombs. So 1.2 millicoulombs divided by 1.602 times 10 to the minus 19. And it comes out to be 7.49 times 10 to the 15 for the number of electrons. So, what's a trillion? 10 to the 12th, and so this is a quadrillion. So about 7.5 quadrillion electrons, yeah. So technically the charge is negative, yes. So, I mean, depends on what I guess I'm talking about here. In my case, I'm got a current that actually then would be going this way in this diagram, right? The electrons are moving from here to here. Okay. And so back here, when I say how much charge, I guess it's the opposite of the direction of the current. And when I then have a negative there and a negative there, you know, my signs all work out. But I kind of indirectly just avoided the minus sign and said, hey, let's just look at positive numbers. All right, well, moving to maybe yet a different example. I think you can see, like that problem there was a lot easier than, say, Gauss's law, where you had to do a Gaussian surface and you had to do an integral, or adding up a bunch of rings of a hemisphere to figure it out. So what I was saying earlier, I think you'll find the application chapters a little bit easier to do. Switching topics then, or not topics, yeah, I guess the idea is let's look at resistance. I picked that one because that was a good one, I think, to, again, see on a conceptual, as well as a little bit of mathematical, but not too hard of math, to see what really is charge. And charge is flowing charge. And so we just had to figure out how many of them do we have here. Whereas this one is about resistance. And so let me read this one. Number 13 says, suppose we wish to fabricate a uniform wire from 1 gram of copper. If the wire is to have a resistance of 1/2 ohm, and we want to use all of the copper, what must be A, the length of the wire, and B, the diameter of the wire? Okay, so here's the idea. The idea is we are going to make a wire. We're going to make it out of copper. The goal is to make it with a resistance totaling 1/2 ohm. The whole mass is 1 gram. So the piece of copper has to have a certain length and a certain cross-sectional area. And so how do we make it? Well, obviously you can kind of see the trade-off here. If you're limited to 1 gram, if you make the thing narrower, then you have to make it longer to use 1 gram. And of course, as you make it narrower, the resistance goes up. And as you make it longer, its resistance go up. So it seems like we should be able to get a whole range of different resistances depending on what we're trying to do. And so I would do something like this. I would start with the idea that the resistance is the resistivity times the length divided by the area. That I'm going to know for sure. Now, we also learned that it changes with temperature, which is what we're going to look at next. So that doesn't really have it up here, and the author probably should have done a little better job by saying this should be the resistance at room temperature. It doesn't quite say that, but I'm going to read that into the problem and say that at this first step, I want this to come out to be 1/2. And the resistivity then, I can, scan back here to in chapter 27 in table 2, where it says, let's look up the resistivity of copper. And it says it is 1.7 times 10 to the minus 8. So 1.7 times 10 to the minus 8 ohm meters there. And this is 1/2 ohm. So what I know is 2 of those 4. That is, I know the resistivity, again, assuming it's room temperature, and that's what the chart lists there, okay? And then I know the total resistance, but what I don't know is I don't know the length of this wire, and I don't know the cross-sectional area. However, doesn't that give me the volume? And so keeping this equation in mind, but also keeping in mind that the product of those two, the cross-sectional area and its length, would be its volume. Okay. Now, I don't quite know the volume, although I kind of do if I again, go over here to density. So I'll come over here and say the density, which is mass per volume, can also be used here. And that's where you're going to have to probably go back a few chapters. And sure enough, back in Physics 121, if you recall, back in chapter 14, we listed all these densities. Density of... Huh?
Two different rows in one problem, resistivity and density.
Oh, good point. Yes, this row is the resistivity, so good. Let me make that clear and get rid of it so it doesn't confuse with this row. This row is the density. In fact, maybe it's probably best to then just kind of spell that out. So that V and volume, and maybe I should do that also, because V here is for volume, not for voltage. Although I don't think we have voltage anywhere in this problem here. So, but I guess we had this discussion last time that there's a lot of symbols and we can easily confuse them. But volume then would be the mass divided by the density. And I know that the mass is 1 gram. I'll pause on putting the units in there because I want to make sure I look them up in the same way. So back in chapter 14 it says density of common substances, and here it is for copper, and they listed in kilograms per cubic meter. All right, so it's 8.92, and so 8.92 times 10 to the third kilograms per cubic meter. And so my mass would be 1 gram, which is a thousandth of a kilogram. So somewhere in here you need to find the volume. So after having done that, 0.001 divided by 8.92 times 10 to the third gives me a volume of 1.12 times 10 to the negative 7 cubic meters. Taking that over to here, 1.12 times 10 to the minus 7 cubic meters, I now have length times area. And so now I can finish this problem by realizing I have 2 equations and 2 unknowns, and one obviously will give me the length and the other will then give me the volume. And I'm not sure how much math I should do here. I'll just go length over area equals, and if I do this number, 0.5 divided by 1.7 times 10 to the negative 8 comes out to be 2.94 times 10 to the, 7. Whereas this other one here, length times area, is 1.12 times 10 to the minus 7. And of course now we have all kinds of ways we can solve this. Probably just multiplying them is kind of nice, because if I multiply these two together I get L squared. And then taking the square root will give me L. And nice thing about multiplying those sides is those go away. So it's really just 2.94 times 1.12, and then the square root of all of that gives me about a 1.81. And this should be meters. Was I careful with my units? Did I do everything in base units? Let's see. This is ohms, cancel off. So doing that in meters and meters, yeah, good. And so there would be the length of it. And of course, once you know the length, you can then get the cross-sectional area by taking, say, that number, 1.12 times 10 to the negative 7th, and dividing it by the length, 1.18 meters, coming up with 6.19 times 10 to the negative 8 square meters. I don't know if they ask us to figure out what that radius is, but we could make the next step. Maybe I'll go back and look here. What do they say here for the question on 13? Yeah, they do say what is the diameter of the wire. So, taking this area and dividing it by pi, and then taking the square root of that, gives me a radius of 1.41 times 10 to the minus 4 meters, or doubling it for the diameter should give me a 2.8 times 10 to the minus 4 meters, or you might like 0.28 millimeters. Yeah, there we go. All right, so fraction of a millimeter. So it's obviously very thin and obviously very, very long. So thin wire, and I don't know if you call it very long, but we're pushing 2 meters here. So there's what we're going to do with our 1 gram of copper, and that would give us a half a ohm. Which, by the way, I should point out, and I did one time before, but want to emphasize it as we get started with this next chapter. That's why something like this, we said at the end of the lecture on Thursday that there is just not much resistance in this. This wire, of course, is clearly much shorter in length than 2 meters, and it is also much fatter in diameter than this one. And so this, probably has 100th of an ohm at most, and maybe even in the thousandths of it. So depending on what we're doing, we often ignore the resistance in our wires. It kind of depends on how much you really want to focus on those details, and if those small amounts of resistance are significant to the rest of the problem, then we better consider it. But in other problems, we don't even want to consider it. Well, let me move into number 20. I'll pick this one next because it was an extension really of this one. Here we took our piece of copper and we just made a long wire and had nothing to do with the temperature range. This one is a clever design. This one says here, listen to this one. It says, an engineer needs a resistor with a 0 overall temperature coefficient. And what they mean by that is, can you design a resistor that does not change its resistance as its temperature changes? No, you think about that way. I keep reading. An engineer needs a resistor with a 0 overall temperature coefficient of resistance. She designs a pair of circular cylinders, one of carbon and one of nichrome. Now, why carbon? Yeah, remember we pointed out there are a few cases here with the semiconductors that we pointed out that when they warm up, although the collision time gets smaller, the number of charged carriers increased. And so we saw on a microscopic level that those contact time or the average collision time was only part of the reason for the coefficient. The other part was how many carriers did we have. And so for things that are the metals like copper and aluminum and gold and even sodium, those have so many carriers already that even when you warm them up, it really doesn't change anything. But it's the ones that only have a few carriers, the ones in the middle of our periodic table, what we call the semiconductors, the carbon, the germanium, the silicon, those three right there were listed on our table. They have only a few carriers. So as you are warming them up, sure, the atoms move more, which kind of stop the electrons from going through, but at the same time, as they are hitting each other harder, they make more charged carriers come off. And so you have more charged carriers, which balances or overrides the smaller collision time. So we actually saw some material that the resistance decreased as the temperature got warmer. And that's the idea of this. The idea here is, well, what if we would do this? What if we would make part of the wire made out of a nickel chromium mixture, that's the nichrome, and the other part of the wire made out of carbon. And so if you were to warm it up, part of the wire, this one, would increase in resistance, but the other part of the wire would decrease. And if we design this just right, we can probably get the increase of one to balance the decrease of the other. And that's the design here. It also allows me to think a little bit more about wires that are hooked in what we call series. This is going to be the first topic we get to as we get started in the next chapter in a few moments, is I'm going to say, well, what would happen if I had a wire? And let me not even worry about what the material is right now, but if I were to look at this wire, it's made out of some material, we'll say rho. It has some length L, and I'll call it total length for just a moment, and area A. Because if you imagine kind of cutting this wire somewhere part way, so that you had length 1 and length 2, and length total then is the sum of those two, we could write this as the resistivity length 1 plus length 2 by using just a direct substitution. The total length is just the sum of the two. Now the reason I say that is because now I can kind of look at the resistance of a long wire as the resistance of the first half plus the resistance of the second half. And maybe I shouldn't say half, because I don't necessarily mean that it's half the resistance or even half the length. What I just mean here is if I have two wires connected one into another, which the word we used for that for our capacitors, and we're going to use again for our resistors, is we'll call this situation series. And so if I have a series of resistors that I hooked end to end, the total resistance, and so maybe I should put total right here. In the next chapter, we're going to call this the equivalent resistance, like we did with our equivalent capacitors, is nothing more than the sum of the two. And so they're asking you to kind of figure that on your own, if you will. They're going to prove it for you as soon as we get into chapter 28, and I am too. But if we have two resistors in series, you just add them together. Note, what do we do for capacitors that were in series? Yeah, it was that harmonic sum. It was the reciprocals added together. So don't confuse the process of resistors in series with the capacitors in series. Okay, so again, more on this when we get started into chapter 28. This is just kind of our teaser into having multiple resistors, but that's really what we have here. And so I can write it this way, that the design for the total resistance of this wire is really to say, what is the resistance of our nickel chromium wire, and add to that the resistance of our carbon fiber wire. Okay? Yes, and then the real key here is we need to design this in such a way that the resistance will not increase or decrease as the temperature changes. Now let's go back and look at some more numbers here. So I'll start from the top here. It says an engineer needs a resistor with an overall temperature coefficient of 0. She designs a pair of circular cylinders, one of carbon and one of nichrome. The device must have an overall resistance of 10. It must be independent of temperature and must have a uniform radius of 1.5 millimeters. And the question is, can she design a wire to meet this goal? And if so, can you tell what the length L1 and the length L2 of each of the materials should be? All right, so reading that, I've come to the conclusion that the total resistance is going to be 10. That's for sure. Okay? And so then I would have the resistivity of the nichrome wire times 1 plus the coefficient for nitrogen times the change in temperature times the length of the nichrome divided by area. Now, let me not put nichrome here for the area because they did say that the two wires are going to have the same uniform radius. So I won't make a distinction between the area for the nichrome and the area for the copper. But I can do the same thing here for the, not copper, carbon. And so I'll put a C here for the carbon, and 1 plus alpha C delta T, length of this carbon fiber or wire over the area. And so that's this design goal here. The whole thing needs to come out to be a 10. All right. So if you look closely at this, we have parts of this equation that has the change in temperature in it, and we have parts of the equation that don't. Hopefully then, mathematically that tells you the parts that don't have a temperature in them must come out to be the 10. The parts that do have the temperature should balance each other, so those together are 0, so that there's no net temperature change. And that's probably the hardest part of this problem, is to just correlate the math with the design criteria of building this. So I would kind of write it this way. I would write it as N of the nichrome times the length of the nichrome divided by the area, plus this one here, rho for the carbon, length of the carbon and area, then plus, and then I put the temperature stuff together. So this right here is rho of the nichrome, alpha of the nichrome, delta T, length of the nichrome over area. And so that's the 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 terms that make up the part that has a delta T in it. Same thing here. Rho, alpha, delta T, L, C over A. And so it is this part that hopefully comes out to be 10. That's the part that has no temperature variation. And so I want it to be 10. Not only at 20 degrees, in fact, maybe you can see it best there. If you talk about 20 degrees, then these delta T's are measured, at least in the table we have. Our delta T is measured from 20 degrees. So if you think about this problem at 20 degrees, delta T is 0, delta T is 0. These two better come out to be 10. And so I'll put a 10 is equal to, and now we can come back over to here and look up these numbers here for the nichrome. And so scanning down nichrome, 1.5 times 10 to the minus 6, 1.5 times 10 to the minus 6 there for the nichrome. The length of the nichrome is still my unknown, but that's hopefully what I will find before this is done. The area of the nichrome wire right here, of course, is depending on its shape, and I think they implied in the problem that it is a circular in shape. I think they did say somewhere in here. Yeah, she designs a pair of circular cylinders. It goes on to say the radius somewhere. Yeah, the radius as 1.5 millimeters. So this would be 0.0015 meters squared would be the area. And of course the other term, the second term here, is the resistivity of carbon. And so scanning down here for carbon, 3.5 times 10 to the minus 5. So 3.5 times 10 to the minus 5. Length of the carbon, pi 0.0015 meters squared. So I'd call that equation number 1, if you will. And of course it has two unknowns, the length of the nichrome and the length of the copper. The other equation would be right here. Why don't I actually factor out a delta T and an A here for a second? Because you can see it, I think, a little bit better. If I take those two terms and say that the rho of the nichrome times the alpha of the nichrome, that's the first two, and then times the length of the nichrome. What?
Both lengths are the same.
No, both lengths are not necessarily the same.
Oh, the lengths are the same.
Yeah. I don't know if the lengths are the same, and I hope they're not the same, because I cannot design what I want if they had the same lengths. So I'll have different lengths to them, and then the other three terms go right here. I don't know if I left myself quite enough room here, but I'll squeeze it in. There we go. And so those have to all come out to be 0. So if those two conditions are met, well, then it works beautifully. If that comes out to be 0, you see it doesn't matter what temperature you put in here. And so basically these two are canceling off here. So if you put in the resistivity of nichrome, which we just had up here, 1.5 times 10 to the minus 6, and then you multiply it by its coefficient, its temperature coefficient, where's nichrome? That's 0.4 times 10 to the minus 3. So 0.4 times 10 to the minus 3, length of nichrome. Then the resistivity of copper, which we already looked up, 3.5 times 10 to the minus 5. And the temperature coefficient, now this hopefully is a negative number, otherwise this is never going to work for this to come out to be 0. We got to have one of those terms 0. But sure enough, it is 0. It is a negative 0.5. Negative 0.5 times 10 to the minus 3. And then we would have length of the carbon piece, and that would have to equal 0. So I'll put a box around it and put a box around it, but I think you can see now you have two equations, two unknowns. I'll leave the math for you to go ahead and say, yeah, we can go through and we can get the how long does the nichrome wire have to be and how long does the carbon piece need to be. And so that's, like I said, what I wanted you guys to see. All right. Well, let me shift gears yet a little bit more here so I can kind of show you as example ones everything we've done. But I think you're seeing that these problems, got a lot of algebra at times, or maybe a little bit of algebra, certainly not an algebra 2, but two equations, two unknowns. So like I said, not to belittle this at all, but our circuit stuff do tend to be pretty straightforward problems compared to, I think, some of the things we've been doing in adding them up in terms of like a bunch of rings to get the electric field, as you guys saw on the test. And so just, I don't want you to put down your guard at all, but you guys really started the first couple of chapters in this class with some hard chapters. And as I said after you guys took the test, I think that the test we just took is one of the harder ones of the whole sequence. And I mean, we still have some harder stuff coming up this semester, but these three chapters, the 26, the 27, the 28, mostly algebra. And we're going to hit some really interesting algebra and a little bit of calculus in the next chapter as we put our capacitors and our resistors together. But for the most part, you'll probably be able to breathe a little bit and to feel a little more relaxed going into the next test. Although the next test will have some more magnetism on there, and we'll get back to a lot of calculus again when I get to our magnetism. So again, I'll leave this alone here and go to number 37, because one of the last things we did in this chapter was to look at power and the energy consumed here. And this one begins to talk about it. This says, in number 37, a certain toaster has a heating element that is made out of nichrome wire. And by the way, this is the second example where we've used nichrome, and you may not be as familiar with that wire, but nichrome is really a nice wire if you want resistance. I don't know if you caught the numbers there, but that resistivity here for nichrome is a much bigger number than it is for copper. And so if you want your wires to have a reasonable amount of resistance, we tend to use nichrome a lot for that. And they handle heat pretty well, and they don't oxidize too much. So they have a lot of nice properties. And any of your heating elements are usually made out of nichrome. And here we have a toaster. So if you look inside your toaster, you'll notice that the wire glows red hot. And of course it's getting hot because of the resistance in it. And so they designed it, and that's what this one says. A certain toaster has a heating element that is made out of nichrome wire. When the toaster is first connected to the 120 volts, now let me pause right there. Why did they pick 120 volts? Yeah, that, if you're in North America anyways, and you plug it in, so anywhere in Canada, United States, Mexico, you plug that into our big grid here, you're going to get 120 volts. Keep that in mind, because you'll see this show up a lot, and eventually the author will just stop using 120 volts and just say, you plugged in the microwave, blah, 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 blah. And they expect you to know it's 120.
If you're in China, it's 240.
I think so. I'm not sure. Really? Because I think it's it's 240 over in Europe, and you say it's 240 in China. I mean, 240. But you're saying it's 360 in Libya? Wow. Okay. See, I learned something new.
Wait, the thing is that I was plugging in an American device with like right or something.
Yes. Yes. And the plugs are different in style. And so when you travel overseas, keep in mind that your plugs will not work. You have to get the adapter plug for it. And so they don't fit. And they're purposely made different. And we actually have the same thing. Anybody have 240 is not the most common power source here in the United States, but we have a lot of 240.
I think it's the common around the world, isn't it?
It is a little more common around the world, yeah. The United States decided to lower it down a little bit to keep the people a little safe. But you lose efficiency when you do that. So it's kind of a trade-off. So keep it high for efficiencies. Yeah. In fact, you'll see that in the next problem, yeah. So part of it you want to keep it high for efficiencies. The other part you want to keep it low for safety. And so there's a balance you come up with.
Isn't 240 used for the big appliance?
Yeah, and so 240 is a common plug. If you've seen them, the plugs are about this big, and they got bigger blades to them when they plug in. Yeah,
They have round blades, not flat.
yeah, and so
Actually, they have different ones. Some of them just have different angles,
well,
and some of them are around
yeah, but isn't the different angle 208?
210, I believe.
Yeah, it's 210 for the curved one.
Yeah,
They're
yeah.
like rounded.
But I think that's a 208
There's
three-phase.
also one that looks kind of like ours, and then it's
Yeah.
but it's like got a
So-
to the other one.
When you guys start working in the industry and you have these power supports, if you're working at a factory or an industrial plant, your voltage is probably 440. And you walk in and you have the 440 powers. And you've got these big, massive plugs. And they all look different, so they don't mess. Well, I didn't mean to quite go down that road. I just meant to say, if you plug it in, what's the voltage? Yeah, if it's a residential house, or like in our classroom or our lab, and we're not a high power industrial area, expect it to be 120, and that's what I wanted to emphasize. Here they tell you, and they'll keep telling you for a couple of chapters, but they'll soon stop doing that and expect you to know that. Okay? All right, so back to the problem. It says we have a toaster. So, you know, it could have been like this morning. You get your toaster, you get it out, you plug it in. As soon as you plug it in, you're thinking, that's 120 volts here. It says when the toaster is first connected to the 120 voltage, the temperature is 20 degrees Celsius, and it has an initial current of 1.8 amps. However, the current decreases as the heating element warms up. Now I'll pause there. Why? Right, we're heating it up. It's going to be more resistance. It's made out of nichrome. You're going to get less current. It says when the toaster finally reaches its operating temperature, the current has decreased from 1.8 amps to 1.53 amps. A, find the power delivered to the toaster when it is at its operating temperature. And then B, what is the final temperature of the heating elements in the toaster? So they're going to ask us to use our electronics to figure out what the temperature is, because we saw it change here. And so if I was starting off here, I would say this is Ohm's law. The current is related, of course, to the voltage and the resistance. And so when I first plugged it in, and so maybe I'll put at a temperature of 20 degrees Celsius, they tell me that I got a current of 1.8 amps. The voltage is 120 volts. The resistance then can be calculated, at least the resistance when you first plug it in. And so if I take the 120 volts and divide it by 1.8 amps, I get the 66.7 ohms of resistance. On the other hand, as it begins to warm up to some unknown temperature, but that's what we will be asked for, then the current drops a little bit. And of course, they're listing a toaster, but wouldn't the same thing happen for a light bulb? So when do you get the most current in a light bulb? So when you first turn it on? It's the most likely time for your light bulb to burn out. When it's got the most current in it. And when's that? When you first turn it on. And so I bet most of you have had experience with light bulbs burning out. And oftentimes that happens when you walk up, it's already cold, and you flip the switch. You flip the switch and it's going to have a lot of current at that point. And now if it survives that massive current at the beginning and begins to warm up, then it's just less and less and less and less current as it warms up. So it's probably going to be fine. Now that's not to say a light bulb can't burn out if you just left it on, and you would. And you probably have had that happen too, that you'll come back to a light bulb and turn it on and it goes, oh. In fact, maybe even you thought it was the off position because the light's not on, and so you walk up to the switch and go, oh wait, it's in the on position. The light bulb must have burned out. So certainly it could burn out when it is in the on position, but it's that likelihood increases with more current. So the most likely scenario is when you flip the switch and then it, and it burns out then. Well, in this case, I have 120 divided by 1.53. And this toaster then has increased its resistance to 78.4 ohms due to the heat increase. So our two questions, what number is this? 37. Our two questions are A, find the power delivered to the toaster when it is at its operating temperature. All right, so the last thing we did in this chapter was to come up with a nice formula for saying this then is the power which you take current times voltage. It also came in different forms. If you applied Ohm's law to it, you could use any of those three forms. In this case, I've already solved enough that we could probably do any of these. But I'll stick to the beginning one because they gave me the current of 1.53 amps. And they also said we're plugging it in, so that's 120 volts. And so 1.53 times 120 is 184 watts. And so that's probably the easiest part of this one. And again, I don't know if any of these are too overwhelming. They do tend to be very physical and conceptual in nature, that you go, okay, where do I go with the math? The math isn't really that hard, but I got to make sure you see that physical picture, like that nichrome and carbon one together is a good example of making sure you see the physics before you can understand kind of the design of it, before you can even do the math on it. The other part is find its temperature. And so we did learn that the resistance does change according to this little relationship. And so I don't necessarily know the length or cross-sectional area of the wire that this toaster is made out of. But fortunately, I can compare what is happening at 20 degrees to what is happening at a higher one, and I should be able to get the temperature difference. And here's what I mean by that, is if I go at a temperature of 20 degrees Celsius, this resistance that we found, the 66.7, must be equal to the resistivity of the wire, which they tell me is nichrome, times the length times the area. Now, we recently just looked up the resistivity of nichrome. I think it's still over here. What was this number? 1.5 times 10 to the minus 6. So if I put in 1.5 times 10 to the minus 6, then I would get at least that much information. And again, that doesn't tell me the length or the area of it. But if I study this equation carefully here at a temperature of, I don't know, I do know that the resistance has gone up to 78.4. And so when I multiply it by the resistivity of nichrome times the area times the length, that would be this first term. And I add to that the resistivity of the nichrome times the temperature coefficient of nichrome times the temperature change times L over A. This should be the increase. In other words, this number here is the 66.7, right? That is the number I got right there. So then if I take my nichrome, which 1.5 times 10 to the minus 6, and I take my temperature coefficient, 0.4 times 10 to the minus 3, 0.4 times 10 to the minus 3, delta T becomes the unknown, and this L over A become a 66.7 divided by 1.5 times 10 to the minus 6, which, by the way, would cancel that. And so, a little bit of calculator work will give me the temperature rise. What is this new temperature. And so again, we're using our change in our current to figure out what the temperature is. Very common. Most of you probably experienced that already unknowingly as you maybe looked at the temperature given to you by your cell phone, your watch, your computer, your car's computer, just to drive down the road. Probably busily monitoring the amount of current that flowed through an electronic device so it could tell you what its temperature is. Not so much that it can tell you, but it probably does that on your dashboard, but it's more interested in what the temperature is so that it can fine-tune the efficiency of the fuel so that it can operate the car a little bit better. Oh, no. The area is not. I'm using this equation. This ratio is the same as this ratio. And then I'm doing a direct substitution. Yeah, no, I wasn't. No. Yeah. Sorry, maybe I did too much math there. Yeah. And that's a long way of saying I have no way of solving for the length or the area, but together I can. So the length of the wire and the cross-sectional area. Yeah. Okay, so solving this, I've got 78.4 minus 66.7. And so this increase is 11.7 ohms. So if I then divide that by 0.4 times 10 to the negative 3, and also divide it by 66.7, I get a temperature change of 439 degrees Celsius. And so it gets quite warm, which was the whole point of a toaster oven, right, is to pass current through there, a lot of current, have some resistance, get it hot, it begins to glow red hot, and it toasts your toast, right? And but how much that resistance change is connected. It also, I thought, would be a good moment to say that's why, you know, for most of our metals, particular things like our copper, which is even less so than the nichrome, not only does it have less resistance, it has a lower temperature coefficient, and between all that is, again, don't be surprised as we work with just copper wires if we say, they don't have any resistance, and oh, they've warmed up, but so what? You know, I mean, it does need to be a significant warming up before we give it too much consideration here. But the physics is still there, and that's the lesson here. All right. All right, here's a good one on efficiencies, number 46, and then we'll probably wrap it up here to go into the next chapter here. But number 46 says, think about the power that's delivered to your house for a moment. It says here, an electric utility company supplies a customer's house with main power lines that are at how much voltage? At 120 volts. Good. So they're still telling you. It is made of 2 copper wires. Each of these copper wires are 50 meters long, and they have a resistance of 0.108 ohms for every 300 meters, which just seems like kind of a weird way to label it. How much resistance per 300 meters, but that's the way it's listed. A, find the potential difference at the customer's house when the customer is using 110 amps of electricity. And then there's some other questions, but I'll pause right there to maybe stop and think about what are they asking here? Well, there is a house yeah. Okay. and a utility pole, where if you look closely at your house, you will have power lines going usually kind of in the backyard area or behind the house. Now these tend to be really high in voltage. I know by my house they're at 16,000 volts. So that's not what gets fed directly into my house. Well, this is the part we talked about earlier. You want to keep the voltage high because of efficiency. And you'll see that here in the problem in just a second. But somewhere you probably will find what looks like a little metal cylinder. And we're not quite there yet, but soon when we get into magnetism, we'll talk about magnetic fields and the whole point of this metal box and how it works. But it's called a transformer, and the design is to take the power, the voltage, that is in this case really high, dangerously high, that we don't want to get near people. That's why we put it really high on these poles way up there, so hopefully nobody will touch it. So somebody with a kite or a metal balloon starts playing with it, or okay. We'll spread it really far apart so when a bird lands on it, hopefully the bird will touch only one wire and not the other side, because what would happen if you touched one
Burns, and then you have a fire.
and then the other, right? And so there could be a long distance. I know by my house those crazy squirrels run up and down here. Whatever the heck a squirrel looks like. And they jump the wire. And I'm just thinking, boy, one of these days there's going to be a squirrel with a long tail and a long reach and just electrocute itself. But
Or a foggy day. Foggy day and it sparks.
it's got to be pretty foggy to spark on a foggy day, but it has been known to happen. In fact, there's been some unfortunate, especially in the area we live, because the reason these are put so far apart is your birds can't reach that far apart, even your big birds. So you have the, I saw a hawk out here the other day actually going across the bridge sitting on that wire. Actually, that one always concerns me. You see how close that wire is on the bridge?
Yeah.
The bridge down to the library? Yeah, I mean, that thing's got to be 32,000 volts. I mean, if you're on the street level, it's way up there. Nobody's going to touch it. But every time I go by on that bridge, I go, man, that's, I could take an extension pole. Fortunately, I won't. But, and touch it and, electrocute myself. It's not that high up there. So maybe I shouldn't tell you. Somebody's going to try it now. Don't touch it.
Don't they put some sort of coating on the wire?
No, there's no coating on. Too expensive. I mean, why would you spend millions of dollars on coating? I mean, one person's going to die.
Wait, what's the wires made of exactly? I mean, it don't look,
But stainless steel mostly.
but steel is not very good conductor.
No, it's not, but it's real cheap. And you got to go hundreds and thousands of miles across the country. That's why, again, you're going to see in this problem kind of the lack of efficiency, the loss of energy. That's why half the electricity generated in this country is used up before it even gets to the house or the school or the residence that it can be used.
That you're going to make it out of is going to be very.
Well, right, and that's why we talked about the superconductors last time. It would be nice to replace all that with superconductivity. So,
It would be expensive anyway.
well, it would be expensive. So it's not going to happen anytime immediately. But maybe a major discovery will take place. As I said before, that'll be your discovery, that'll be your Nobel Prize, that'll be your millions of dollars, that'll be your donation back to the school, and I like my Ferraris red, and so this is this, like I said, this problem. So they're designed this way. The only interesting part about this is there's only one bird actually big enough, and it's that California condor. And so that's the unfortunate bird that keeps electrocuting itself. And so as we spend all these millions of dollars in the Los Padres National Forest to bring the birds back, and actually it has been successful, but they keep electrocuting themselves as they sit on the wires, and they also eat the lead bullets that people shoot up there. So between dying of lead poisoning and electrocuting themselves, it's been a challenge to bring that species back to life. Yeah, they like to eat shiny things for some reason. So those of you who might be a little more interested, that's why, yeah, just last week, Governor Brown had a bill on his desk that was, gonna outlaw lead bullets. And a big push of that was for the California condor. But it's not just the California condor, it was everybody, because, how much lead do we have around in our national forests because of practice shooting and hunting and all that stuff? We don't really know. So that was part of the idea of getting it. So then people would shoot brass bullets. So, but supposedly the California condor doesn't eat the brass bullets; they only eat the lead ones. So, anyway, I didn't mean to get sidetracked on there, but this is kind of the design. And actually, as long as we're mentioning it, I have seen birds line up. And then electrocute themselves. So that has happened, and so they'll just put too many birds on there and they'll short circuit. So. And as long as we're bringing it up, I've seen black bears, who come out of the mountains, Ojai, Monrovia. Those are good places where bears often show up in residential areas. Sierra Madre, for some reason they love those areas. They come out of the hills, and of course then they get spooked, and so they get chased up, and it's often a utility pole, and then they get up here and they sit and touch the wires and electrocute themselves. And fortunately, I guess they're big animals. They don't actually usually die when they get electrocuted. They just wounded real bad. They fall, yeah. They put them in the little truck and take them back into the mountains. And hopefully they don't come back. Anyways, sidetracked over here, but here's my point. My point here that I want you to see is the power lines will be at a very high voltage. The big metal ones, not the ones that you will see in the city, but the big metal ones, and you can see them here in our hills going on up out into the forest and across the desert and out to, we get a lot of our power from, say, Hoover Dam, and going across the desert. The big metal ones, the ones that are super tight, that's a 500,000 volts. So they deliberately have put them, at a higher voltage. And that's kind of what I want to have you see in this problem of the advantage of the higher voltage. And of course, the danger of the higher voltage. For us, though, where in your backyard, maybe 16,000 or 32,000, they will go through this little transformer, and that will reduce it down to 120 volts. And so that's the value that is coming out of this transformer and going to your house. And actually, it usually feeds to 4 or more houses, because the pole will be, here's a bunch of lots. And so you have a street and a street and a house and a house. And if you put the utility pole right there, it can easily feed 4 homes like that. And so you've got these 4 sets of wires coming from the transformer. Each of the 4 houses are getting 120 volts. They'll even tie them together. You'll see some wires low on the pole connected to the other pole. So those lower ones are the safe values, the 120.
Is it high voltage because of high resistance or high current?
They generate it at a high voltage. And so I'll say neither to that. It's high voltage because of the magnetic fields in this transformer, which we haven't talked about magnetism yet. But why is the high voltage of even an interest if we are going to end up electrocuting ourselves or birds or bears or whatever? Is because think about the power that is delivered. Wouldn't it be the current times the voltage? So if you wanted to run a whole city like Santa Barbara, and you've got these power lines coming in, you've got to either have a high voltage or a high current, right? Or many lines, right? And so we have all of the above, but here's the real point of this, and actually the point in this calculation. As the wire runs from the transformer to the house, there is going to be a change in voltage according to Ohm's law. There's going to be a reduction in voltage. And that's what this problem is after. This problem is saying that that wire, which is 50 meters long, doesn't have much resistance at 50 meters. But if this wire is hundreds of miles, that could be a lot of resistance. And in our case, they said that it is 0.108 ohms for every 300 meters. So if I take that ratio and then multiply by my 50 meters, you'll see there's not much resistance. 0.108 divided by 300 gives me the resistance per meter. Then when I multiply it by 50, you'll see that that wire coming into my house doesn't really have too much resistance, and I just live with that resistance. I don't try to make it out of copper or silver or anything else that is kind of expensive and worry too much about it. But that would be my resistance for this wire. So, as I think about the reduction in voltage, that is, what is the loss of voltage as the charges then move through here, I would have a current, which they said I've got 110 amps, which sounds like a lot. I guess we have to have everything on, so all the computers, all the TVs, all the lights, you know, refrigerator. I suppose if you have a heating you know, one of these all-electric houses, it's probably not too much. But you know, I've got both ovens on, and you know, it's an electric oven, and got the microwave on, garbage disposal, running the table saw, and the air compressor. All right, but anyway, so I got everything going here, and I suppose that might not take too much to get to 110 amps. But here's what the author and what I'm trying to get you to see. If I take that much resistance and I multiply it by 110 amps, I actually get somewhere in the neighborhood of about 2 volts. And so I have lost 2 volts. Not that much. I mean, it's 120, I lost 2. That's, you know, less than 2%, somewhere just a hair less than 2% coming in. But remember, that electricity has to go through my house and do whatever it needs to do. Let's say run the vacuum cleaner. But then it's got to do a return line. And so there is a similar loss of voltage there. So if you're telling me the transformer is 120 volts, and I'll call this side 0, that means coming out of my house, this needs to be 2 volts. Going into my house is 118 volts. My house then is only seeing a difference of 116 volts. Each wire is consuming 2 volts. And so there's a loss of energy coming in, and then loss of energy in my house, which that's good because that's what I'm trying to do. I'm trying to actually use that energy. Then there's a loss coming out. So I wish I didn't have those, but that means my appliances are only running on 116 volts, even though they said I was getting 120 volts. And so you can imagine that if this wire is longer and longer and longer, and so what if instead of being 50 meters away, you're 100 meters away, 1,000 meters away, 10,000 meters away? There's just no way that you're going to get anything useful if you run a wire for 10,000 meters to a house at such a low voltage and high current. And so that's why, as it runs through your backyard and it runs through the desert, it is not at a low voltage. It is at a high voltage. And then we'll use a transformer to step it down before it comes, you know, near people and it's dangerous.
So why would you measure the sending high voltage through a wire instead of sending high current through a wire anyway? Because of the power voltage?
Because what you lost, yeah. the loss of voltage you are going to get, right? You want this number to be small. Now, small, but yet still have some to deliver the power. So there's a trade-off here, right? Part of us, we want it small because we want to get as least current and as least loss as possible in our wires. But yet big because we want power. So the truth is, you can still get a lot of power if you have a high voltage and very little current. And then if you have very little current, you have very little loss. And so that's why, again, we'll string these wires 300 miles from Santa Barbara to Hoover Dam, and we'll set the voltage at 500,000 volts so that the current would be small, but the voltage would be high. Not to say there's not any losses, because there certainly is.
What are the advantages of the return wire? Why have a return wire?
Well, you can't make a circuit without a return wire, because then you just put electrons in and they pile up and it becomes like a capacitor and it stops more from coming in. Yeah.
What if in the house we have more resistance, or like we're using up more energy than the 116 volts, and then there won't be enough for it to go back to the, like, you know, to complete the circuit?
Well, no, you can't. You couldn't do that. The physics wouldn't allow that. What would happen is you would, you may want to use more. And maybe an air compressor is a good example, because many of the air compressors are right at the power limit. That is, they can run on 120 volts, but they can't run on 116 volts. So if you had a long wire going into your house and you plug in your air compressor and you flip the switch, it won't start. It just doesn't have enough power to run. It'll just go, bleh, you know, kind of thing. And unfortunately, at my cheap, simple house, it happens all the time. And actually, this works fine in my compressor as long as I plug in. In fact, my compressor even has a cord on it that says, do not use extension cord. I mean, the plug on it is annoyingly small. It's about 3 to 4 feet. And you got to plug it in right to the wall, because if you lose just a little bit of voltage, it's right at the edge. It won't work. And I plug it in. If I put an extension cord on it, it doesn't work. So if you as long as you want to use your compressor next to the plug, it's great. Of course, the alternative for an air compressor is then you just use air hoses. So if I really want to use my air compressor for, say, my air tools, and those are out in the driveway, but my compressor's in the garage, I just have a long air hose. So that's how they still work. You just got to keep it close to the wall. Yeah. But yeah, I'll never forget when I first got it and I got the plug out and it said, do not use extension cord. I was like, what? So of course the first thing I had to do was get an extension cord to say, well, why not? I kind of suspected. And sure enough, no. Even with a good thick extension cord, it just won't work. So it just barely operates. And then I guess that's the consequence of living in an old house. This, you know, the wiring for an old house was not built like today's standard of electricity is. Well, I didn't mean to talk quite so much on that particular problem, because I wanted to get right into the next chapter and leave you with a hint. So I will leave you with a hint. You have probably the most challenging one for the homework. You can see the ones I did that hopefully they aren't too challenging, although I must say they are very physical in nature, that you have to see the conceptual picture to work out the math. So if you don't see that, you will struggle. But once you do, the math tends to be fairly straightforward. The hint I want to give you, the hardest one I think, is the magenta one. It's number 56 and 57. Are you doing both of those? Yeah. They're really one in the same. We learned that if you had a wire like this, that the resistance is the resistivity times the length divided by the area. Fair enough? So this one is going to require you to think a little bit. What if you have a wire that diameter is increasing. Or your other problem has more of a wedge shape to it. And says, what if, oops. What if you have something that has a height of y1, but the height increases to y2? A certain length and a certain width, and that doesn't change. But the point is, the cross-sectional area is changing. And in here, the cross-sectional area is changing. Fair enough? So here's my hint for you. Yes, it involves a little bit of calculus. Let's see, how does the resistance change with length? I like to write it as a dx. And so what this is saying is a little of resistance, and hopefully it's not a surprise here, but a little bit of resistance would be the resistivity divided by the cross-sectional area at that moment times that length. And so if you looked at a little cylinder piece right here that had a thickness of dx, it of course would also have a radius, and that radius would turn into an area. And so hopefully what you're noticing here as you move along the wire, this part of the wire, having a bigger radius, would have less resistance than this part of the wire. But to find out the total resistance, you could think of this as a cylinder plus, or maybe disc, I should say. Disc plus a disc plus a disc. And so we could add up all of our discs. Or in something that looks like this, we could add up a bunch of rectangles. And in our case, we are adding from the beginning of the wire, let's just say the wire had length L, we would be adding from 0 to L, but of course this right here, A, is a function of X, right? The cross-sectional area depends where you are in there. And so you're going to have to write that equation. I would maybe make a grid here and realize that if this is a line, so y equals mx plus b, and then that would be the radius, and you square it, you would get your area. So your area would be pi times y squared, and y then is an mx plus b, and square that, right? So that's how I would set it up. You could, at that point, do anything more that you want. But the point is, the area is not a constant as you add up along the x. The material is, so you can just pull that in front, but that one changes. And so that's my hints for, I think, the two magenta ones that are on your homework this week. All right, well, with that said, in the hour that I kind of missed here, let's look at circuits a little bit more. Let's jump into chapter 28 and take a look at a more complicated set of circuits. So let's just keep building on what we've learned here in chapter 27 and start to put multiple resistors together. And that's about as far as we'll get today. But your author does kind of put this chapter into three parts. He says, let's look at multiple resistors. Let's look at resistors and capacitors together. And let's take a look at batteries, and particularly batteries on the internal side. They'll have some resistance. And that you kind of saw last week in the lab. So we'll do that last. So we'll end up doing that Thursday. But I'd like to do multiple resistors first because you probably won't be surprised. Guess what you're doing in lab tomorrow? Multiple resistors. And so you're going to do a lab similar to what we did with the capacitors. You might remember that in the capacitors lab, what we did is we took a bunch of capacitors, and first we measured them, what were they individually, and then we put them together in series and parallel and combinations thereof, and you were asked to both calculate it and measure it and see if they match, and that's exactly what you're going to be doing this week in lab to get a feel for multiple resistors. So let me do this. Let me start with the easiest case here and say, let me take a battery. Oh, I don't know why I use that symbol. Well, this is mostly what we've been doing for a battery. A slight variation is this is called a multiple cell battery. So this is one like your car battery where you don't just have one set of chemical reactions, but one chemical reaction leads into another, leads into another, leads into another. So I'll just do a multiple cell battery for whatever reason. But let me hook up resistor 1 and resistor 2. And so if I call this V for the voltage, then as we study this, and a continuation of what we just learned, is we would say the following. We would say that the electrons come out of the negative on the battery and they get pushed through. That, of course, means the current dq dt is in a direction opposite to the movement of the electrons, right? That was the big discussion we had there in chapter 27 we just got done with. Okay? And so the current would be flowing. But we kind of just touched on this a few moments ago. Could this be thought of as the same power supply but an equivalent 1 resistor? You see, because if it could, wouldn't that tell me the current is then just V divided by that equivalent resistor? Couldn't we just apply Ohm's law to find out what the current is? And so the same game we played in chapter 26, where there was some nice, easy calculations when we did the equivalency, we're going to see the same thing. There will be times where looking at the equivalent resistance is very useful. And this is one case of that. Now, probably doesn't surprise you that the equivalent resistance comes out to be, R1 plus R2. You can hopefully see that if we think about the physics of what's going on. This process is referred to as series. Let's stop there. What did we mean by series again in chapter 26? We're going to continue to hear. What do you mean when you say something is in series? They have what? They have the same current. If you look closely at these electrons, or if we want to stop looking at electrons and now start looking at current, goes through resistor 1 and goes where? Has no place else to go. And we learned on the very first day of the semester here, we learned a principle called conservation of charge. We learned that these electrons are not created or destroyed. And so when we did the rubbing way back when we started chapter 23 and we took the paper and the vinyl and we rubbed it and we said the vinyl collected electrons, where did they come from? They moved from the paper. We didn't create them out of nowhere. And we're going to be saying the same thing here. That this conservation of charge means that if 100 electrons come down and go in here, that means 100 have to come out. That means 100 go through here. That means 100 go through there. And so the current in number 2 is the same as the current that goes into number 1. That's a conservation of charge argument. Okay. Now, the other nice principle we've learned in our past chapters is conservation of energy. We said this. if you can imagine yourself being inside the wire, we're back to that little magic school bus again, and you get down on the magic school bus. So I'm talking about me in the wire. I'm not talking about the movement of the electrons in the wire, but me in the wire. If the water analogy helps, think of this then, okay, this is the energy source. This is the water pump. This is what gives the water its energy. And the analogy I was using last time is this might be a water slide. And so the water flows and then loses its energy. It goes downhill. But the loss of energy downhill has to be the total amount as the uphill, doesn't it? The water doesn't come back halfway and the water doesn't go past it and magically reappear up here. The conservation of energy means that if you go up, you would also have to go down. If we get away from water and consider this a little mountain hike, if you park your car right here on the trailhead and you take the part of the trail that goes uphill first and then downhill, you will go downhill the same amount you went uphill. If you go the trail in the other direction, then I guess now this is uphill. And this is now downhill. But you will go up as much as you go down. And so what we like to say is if you go around a loop, you got to get back to the same place you started. Your change in voltage as you go up and as you go down, if you get back where you started, according to conservation of energy, you better end up at the same place. So your total change in voltage all the way around a loop has got to come out to be zero. That's a conservation of energy argument. And we're going to do that again and again throughout this chapter. That is conservation of charge and conservation of energy. Okay? And it was Kirchhoff who made these arguments. So we'll refer to these as Kirchhoff's rules, but they are conservation of charge and conservation of energy. More on those in a second here, but let's just look closer at this resistor. Here's what I'm saying. I am saying then that if I were to add up the voltage, there would be an increase here of V. There then would be a decrease of current times R1. There then would be another decrease of IR2, and that total change would get me back to 0. Okay? So if I were to solve this equation for current, I guess I would take these two and move them over to here and factor out the I, and I would get voltage equals resistor 1 divided by resistor 2. And so now, if I compare this guy, the equivalent circuit, with the real circuit, hopefully you can see that the equivalent resistance is just the two added together. And so there will be times where it will be nice to take two resistors, put them together, and think of them as only one. Makes your circuit a little bit simpler. And as I said for capacitors, equivalent circuits are nice, but only useful if they lead you back to some information to the original one. And you'll see that. It is, yeah.
Why don't we write our I epsilon naught for this equation? The inner resistance for the...
You mean an internal resistance for this battery? Okay, a good point. And we started to do that in the lab. And actually, your author starts to do it right away at the beginning of this chapter. I thought I'd wait a little bit, but as long as you're asking, remember that this battery is made out of some materials. Let's again, to say it's a car battery. So it has sulfuric acid and lead in it. And so for the current to flow through there, we probably need to model it a little bit better to say there is also some resistance there. And so this is not complete. This would need another term, I think is what you're saying, of a third resistor in there. And I'm building up to that. I just wanted to do two on the outside before I did one on the outside and one on the inside. Just put two on the outside together. Okay? So I'm not doing any internal resistance quite yet. And I think we'll run out of time for that today. But that'll be the first thing on Thursday. Yeah. But what I wanted you to see is if you have two resistors in series, this is the equivalence. Probably doesn't surprise you then. What about our other option? What if we built a circuit that looked like this? Now I'll start off with the name. What shall we call this? Yeah, so this is parallel. Why the name parallel? Again, just like we did for the capacitors, so if you missed it with the capacitors, catch it now, is unlike the series, and maybe I'll go back to the series means that the electrons go from one into the other. They have no other option of where to go. That's not what happens here. What happens here is the electrons, as they come out of the battery and as they are moving along, they get to this place where the wire splits. We're going to refer to that as a node. Okay, so at this node, some of the electrons would go this way, and some would go that way. And again, just like our capacitors, I'm not saying that they're going to split 50-50. What would determine how they split? Well,
How much voltage each?
right. The voltage is going to be the same. Because what you're saying here is this, going back to our water analogy, is our pump. So again, if this is a water park, if you think of this as your pump, that's bringing the water up. And as the water gets up to the top, there's our current, it gets to this node, and the water then can divide. Some of it may go down slide number 1, and some of it may go down slide number 2. But I know this, that no matter which slide it goes down, don't they go down the same amount. And so when we write this as voltage, voltage for number 1 is the same as voltage for number 2. See, that wasn't the case over here. I never said that the voltage on resistor 1 was the same as this. In fact, it couldn't be, because the voltage on number 1 is here, and the voltage on number 2 is here. What I was saying here is the two voltages together add up to be the total voltage. But the current is the same, and that's almost the opposite of what we're saying here. In this scenario, when they're in parallel, we're saying the voltages are the same, but the currents are not. In fact, maybe I should write it over here. Over here, we are saying the currents are the same. The voltages are not the same. And again, we have the wires hooked up differently, and so the behavior is different. So the equations are different, and that's what you're going to have to recognize. And so just like the first test, on the second test, you're going to have a circuit. You got to look at the circuit. You got to decide, are my resistors in series or are they in parallel? Because you're going to want to do an equivalency on it. And to do the equivalency correctly, you have to recognize, are they in series or are they in parallel? And you saw the same thing on the first test. Most of you recognized whether they were in series and parallel, but there were a few of you, as you probably, only you know if you were one of them, you looked at those capacitors and you said, oh, I put those two in series and they weren't really in series. Or I put them in parallel and they weren't really in parallel. So the reason I'm pausing here is to make sure you recognize when are two resistors in series, or for that matter, two capacitors in series. When are two resistors in parallel, or two capacitors in parallel. So again, they're in parallel when they got the same voltage. They're in series when they have the same current. And because of where the electrons can flow, because of how the wires are hooked up, they can behave very differently. But I would say that this does have an equivalency. Those two can be hooked up and thought of as just one resistor. And here's what's nice about that. When you think of it as just one resistor, then the current would just be the voltage divided by that equivalent. And so if you can find the equivalent resistance, you can quickly find the current. And that may or may not be helpful with the real circuit. I'm not sure in this case the equivalent circuit would actually be of any use, but nonetheless there are times where the equivalent one will help me solve the real one. And so, what is the little formula, if you will? And the real key then is to focus back and say, well, this is going to have some current. I labeled it here as current. Let me call it total current for a moment. And the reason I say total current is because as I come back here, I'm looking here at total current. That's what's coming out of the battery. So how does this circuit compare to its equivalency is, well, what comes out of the battery here is going to be the same as what comes out of the battery here. But what do you notice right here when it gets to this node? Yeah, it splits, right? And so I will call this current number 1. I will call this current number 2. I am not saying at all that the current splits 50-50. What I'm saying is it will split in such a way that the voltages are the same. But the real key to this is, what do you know about current 1 and current 2? This is our conservation of charge, right? The whole argument we used back here that said that the current in one resistor has to be the same as the current in the other resistor is whatever electron goes through one has no other place to go. You can't create or destroy any of the electrons, so whatever goes through one follows into the next one. And what I'm saying here is just like water at our water park, however many water molecules you have here, they will split. But if you add up the water molecules going down this slide and the water molecules going down that slide, the sum of those two better add up to that one, because we don't make any new water molecules at our water park. And likewise here, we don't make any electrons here. And so the idea here of conservation of charge leads to that idea. And so again, conservation of charge over here gave me the same current. But conservation of charge here tells me that the total current is the sum of the two. And then what's nice is if I apply Ohm's law here, this would be the voltage on 1 divided by the resistance on 1. This would be the voltage on 2 divided by the resistance on 2. This current total can be thought of over here with our equivalent circuit. So this would be voltage over the equivalent circuit. You just told me earlier on that all these voltages are the same, so they can cancel off on both sides of the equation, and we get what I'm looking for, and that is, how do I calculate the equivalent resistance when I have resistors in parallel? And so there, and maybe I should have put a box around this one and this one, there are my two equations. Notice, though, that these are opposites of what we did for capacitors. So be real careful with that. Remember when we had capacitors in series, we did the reciprocals? Notice when we did capacitors that were parallel, we just straight added them. And so there's a different relationship here. And that's easy to miss. Although it's easy to trace the reason for it, the resistance has to do with the area on the bottom. Capacitance has to do with area on the top. So the reciprocals of each other. So it doesn't surprise me that the size of the area and what physically happens are the reciprocals of these two devices.
For the first circuit that you have in series, you could write the 3 capacitors as one equivalent.
Yeah. Right.
And that would be just the reciprocal. Because they're in a series.
They're in series. Are you adding resistors or capacitors?
Capacitors.
Yeah, right. If they're capacitors, then I would add reciprocals, yes. Now, here's my point then. And maybe there's just enough time to show you one example, though I'd really like to make the next step. And well, maybe I will. So I'll do one quick example and then come back to more examples on Thursday, but it'll also lead to the other issue I want you to see, just so that you're more ready for the labs tomorrow. But the reason for me showing you all this is the same reason we did it for capacitors. It is, what if you had a complicated circuit, one that looked like this? You had a voltage hooked to a resistor number 1, which then came to a node and split into resistor 2 and resistor 3. That recombined and went over to resistor number 4 and then finished the circuit. Could you tell me the voltage, the current, the power on each of those 4 resistors? Right. And so let's run through this again like we did for our capacitors. Let's make a little table here. I will put R for our resistor, R1, R2, R3, and R4. And maybe just to keep the math and the organization a little bit simple, I'll just say, let's call them 1, 2, 3, and 4 ohms. Okay. Could I then get the current in each, the voltage on each, the power on each? And of course, I'm showing you with 4 resistors, but could you do it with 5 or 6 or 7 or a billion? Well, depending on how the billion is hooked up, I hope so, right? And so this then is done by equivalency, if you have equivalency. And I should emphasize that, because the second half of this chapter is to remember that resistors are sometimes series, they are sometimes parallel, and they are sometimes neither. So obviously if they're neither, you don't want to be drawing the equivalency, because there is no equivalency. And so we need to talk more about the neither case. But I think at this point in your education, we have done so much talking about series and parallel, it often comes across to students as they're either series or parallel. There's nothing else. And that's not true. There is neither, and we need to go forward with that. We didn't do much of the neither case when we did capacitors. We were just learning. Now we're one chapter more advanced, and so now we'll talk about the neither case here. But as I would hook this up, I like to then just kind of draw and say, is there anything I can do that would combine 2 or more together to simplify this? Is there anything this is equivalent to? And I'm hoping you see it. Do you see R2 and R3? Are they series, parallel, neither? Yeah, they are parallel. What's the requirement that they be parallel? Yeah, they have the same voltage. They don't necessarily have to be drawn as 2 parallel lines like in geometry. They're not drawn parallel purposely, just like on the test. They weren't drawn parallel purposely. So you would think about the electronics, not the geometry of it. But these are parallel. And the easiest way for me to remind myself if they're parallel is to remember that a wire is an equipotential. And so if I draw that wire that connects resistors 1, 2, and 3 together in blue, everywhere that I have blue has the same voltage. If I do the same thing on the wire here that is on the other side of number 2, and I draw it in red, then I can see a little better visually that the voltage difference from number 2 is blue to red. Blue to red is also on number 3. And so the change in voltage of number 2 and number 3 are the same. Now, 4 goes from red to something else. I'll just leave it as black. And then there's a change in voltage, so maybe I'll go orange here. But number 1 goes orange to blue, and there's nothing else that goes orange to blue. So there's nothing else that's in parallel with number 1. And 4 is red to black. There's nothing else that goes red to black. So nothing is parallel with that one. But I can simplify that and have an equivalence. And that equivalence, since they are in parallel, is the, well, I erased it, but it's the reciprocals. So it would be 1 over 2 plus 1 over 3, and then I would take the reciprocal. And so kind of my first step in solving this would be to say 2 reciprocal plus 3 reciprocal equals reciprocal of that, and I get 1.2. And then, continuing down this road, looking at this circuit, which of course is the equivalent of this circuit, but this one's a little bit simpler. What do I notice about that one? Yeah, they're series. Now again, the best way for me to remind myself in series is series has to have the same current. So the only way something can be in series is if you were to draw a line from one end to the other. That's the only place you could go. There's no node along the way. There's no place for the current to hit something and divide and spread out and become less or more. You don't have an option for those to go anywhere. And so 1 and this equivalence of 2 and 3 must be in series together. And for that matter, this equivalent one and number 4 must also be in series as I draw a line. So all 3 of these have the same current in them. All 3 of them are in series. And so I could just add them all together. So 1 plus 1.2 plus 4 would be the equivalent there. 1 plus 1.2 plus 4. What's that? 6.2? And so this would give me 6.2 ohms for the equivalent of that circuit. Now I guess I didn't give you any voltage to work with, but let's just say this is kind of our standard 5 volts we like to work with a lot here, since that's what the digital world seems to be designed around. So I'll take my 5 volts and then apply it over here and say if I take 5 volts at this equivalent circuit, that'll be 5 volts divided by 6.2 ohms, and I will get the current in this equivalent circuit. So 5 volts divided by 6.2 comes out to be about 0.806 amps. Okay. And now maybe you can see again, like we did for the capacitors, why we're doing this is if you look at this equivalent one, if this is at all helpful to answering this real circuit, then it was worth our time and our effort. And I claim it is. Because this 0.806 is what is coming out of this equivalent battery. Stepping back to the real circuit, then what comes out of that real battery is what goes in number 1. And so I have answered how much current is going into number 1. Now, unfortunately, as it comes out to number 1, it hits this node and it splits into 2 and 3. So I don't know how much current is in 2 and 3. But what do you notice in 4? They come back together. Conservation of charge means we must have that total again, and that's the total that then goes into the battery. Makes sense. What comes out of the battery has to equal what goes into the battery. And so that does help me with this also. And I'll even go one step further. If you know any 2, you can get the third, right? And so as long as I'm here, I will go 1 times 0.108, and that should give me 806. And so that should give me a voltage of 0.806. And then 4 times that is what, like a 32? 3.2, oh yeah, 24, that makes sense. And that would be the voltage there. And as long as I'm working on those lines, I know that the power is these 2 multiplied together. Or it's this square times the resistance. Or it's this square divided by the resistance. But as long as I'm there, I might as well get the power too. And so if I go 0.806 times 0.806, this would be 0.650 watts. Volts, amps, ohms. And then down here, 0.608 times 3.224 is 2.60. Well, should I do 60. And so I guess I'm half done because I've got the current, the voltage, and the power in two of those four. So again, you can see why the equivalent circuit can be quite useful, right? It quickly gave me a way to get the current, and as I compared it back to here, I actually got half the problem done already. Now, the other half of the problem, I probably want to come back and look a little bit at this equivalent one. If you look at this equivalent one, the voltage there must be the same voltage as the 2 and the 3. So if you kind of come back here and look at the current going through this equivalent one, that would be the current going through here. So if I go current times resistance, the current is 0.806. The resistance is 1.2. And so looking at that equivalent circuit can also be useful. 0.806 times 1.2. And I get 0.967. So that's the voltage on the equivalent one. But the whole reason I would care about that is if I look at the voltage on this equivalent one and I come back over to here, that would be the voltage from the blue to the red. So I know that voltage. 0.967. 0.967. Now, to be quite honest, I could have got that another way because I would know that the voltage has to add up to 5 as I went up 5 and then down 5. So that plus that plus that is supposed to be a 5. So I should have got it that way too. And so if I take 5 and subtract 3.224 and subtract off 0.806, I should get 0.97 here. So I don't really have to look even at this equivalent circuit, but I wanted to so that you would see that, hey, we can look at any of the equivalent circuits, and as long as there is something that is useful in that equivalent one that'll help you with the real one, please do. And there's lots of ways to get this equivalent one. And of course, once I have 2 of these 3, Ohm's law gives me the third, and then once I have 2 of these 3, I also have my power. So finishing this problem and maybe not quite getting as far as I would have liked to, let me get the current by taking 0.967 and divide it by 2 to get a current of 0.484. Here, let me take that same voltage, 967, divided by 3, 0.322. Let me just check a couple of things, right? I mean, if this is going to work out right, if I've done everything right, how are we doing on time? If this has panned out, then 5 volts here should be equal to a drop of 5 volts from 1, 2, and 4. 1, 2, and 4, add up to 5. Good. Likewise, if I go up 5 here, 1, 3, and 4. 1, 3, and 4 should add up to 5. And let me emphasize, like I did with the capacitors, I am not saying that all 4 of these add up to 5. Don't fall into that mistake. But what I'm saying is a whole loop would add up to 5, and it does. Also, notice that the current that is going through 2 and 3 should have come from number 1. So if I take the current in 2 and 3 and I add them together, I should get that one there. 6, good. 10, good. Good, right? It does add up. Likewise, those two should add up back to there. Let me check the power. As I come over here and figure out the power on resistors 2 and 3, 0.484 times 0.967. This is 0.468. This one here, 0.322 times 0.967, come out to be 0.311. If I add these together, this is the power being used up on each of these 4 resistors. And so 0.65 plus 0.468 plus 0.311 plus 2.6 comes out to be 4.029 watts of power when all 4 of these are now being consuming energy. Where did they get their energy from? They got it from this power supply. So the power being delivered by the battery should equal the sum of the power then being consumed by each of the 4 resistors, right? And so coming back to the current coming out of the power supply, and a voltage of 5 volts gives me 0.806 times 5, and I get 4.03. And other than a small rounding difference, and my partner made a mistake, it looked good, right? And so the powers do add up as they should. The currents add up as they should. The voltages add up. There is no way I can get that wrong and not know it. Okay? I may get it wrong and know it's wrong, but there is no way with all those options that you can get this wrong and think you got it right. There's just too many directions to go on.